Welcome to Calculus Chat, a weekly discussion with your lecturers for 114. I'm Dr. Biggs, and here with me is Dr. Kellerman
Good afternoon.
and Professor van der Walt.
Hello.
Well, we're not quite weekly anymore, but we're doing our best.
Yes, so the end of the semester is taking its toll on everyone.
Indeed. Well, let's chat a little bit about what's been going on. So, in lectures in the past 2 weeks, what have we done? Well, we did some optimization and covered some beautiful, lovely problems. And I feel just like curve sketching, this is an area that really you get to bring together all your tools to manage the problem, which is beautiful always.
It's also nice being able to put a picture to the idea. It's not just abstract symbols.
Yes, indeed. It's those problems become really tangible, and you can see, start getting a hint about just how powerful these techniques are for doing really nice, important stuff in reality.
Yes, I mean the example in the lectures about the can, the soda can. I mean it's a nice example and of something which is of practical importance if you're in the soda canning business.
Indeed, I've always meant to actually try and take that measurements of cans, like your soup can and your soda cans, and see, do they match that prediction? Is that the thing that they are maximizing, or are there other variables that they've included? But I haven't quite gotten so far as to do the actual comparison.
Well, I did, to be honest, tweak the data in that problem a little so that it comes out to more or less the right dimensions.
Aha. Okay, and well, that finished off our applications of differentiation, and then we started the new theme on integration, right? Which is the basic problem is finding the area under the curve, which is a beautiful idea, and I really love that we build it up sort of from the ground up and use this idea that we've had from the start of a limiting process, and now apply this idea of a limiting process to this quite different problem.
It's really a central idea in a lot of mathematics. This limiting idea, the idea. I mean, it's difficult to solve a problem exactly, so you try and solve an approximate problem, and then try and make the approximation as good as you can, and then in the limit getting the right answer. And this is precisely what you do with the Riemann sum if you want to solve the area problem.
Yes, and we did Riemann sums, but students might be interested to know there are other types of integrals, for example, the Lebesgue integral. So there are some functions that are not Riemann integrable, but they are Lebesgue integrable.
Yes, this gets into when you want to start generalizing things. And I mean, I think we mentioned that our classic counterexample, which is the function that is one on the rationals and zero on the irrationals. That's a classic example of something which is just horrible, jumps all over the place. You can't integrate it. And I think we treated that as a counterexample to show, well, there are functions that are not integrable. But then, as mathematicians do, we like, but can we make sense of integrating this in some way? Can we generalize our idea of integration so that we can assign a number to the integral here in a sensible and consistent way that might be useful? Now, I mean, in terms of my research, I don't actually have to go beyond the Riemann integral. It's fantastically solid for many applications. But of course, theoretically, it's a valuable question to ask. And of course, there are applications for that as well if you go deeply enough into some areas of mathematics.
Well, I mean, that example, so it's not just a matter of mathematicians going, oh, but can't I integrate this function?
Hmm.
It's actually a very important thing because you see, that function you can build as a limit of sorts of a sequence of functions, all of which are integrable,
Aha.
and all of which have integral zero. But then you get that the limiting function is not integrable, and that's a deficiency of the Riemann integral. It's a way in which it is not the right integral.
Yeah. It doesn't play nice in the space of functions, in a sense. And then it makes it hard to do other things in that space.
Yes, exactly.
And I believe that function is Lebesgue integrable.
Yes.
Okay, so that was the basic development, and we introduced the concept of an integral. And then we got to do the fundamental theorem of calculus, specifically part two, which allows us to tie together the ideas of integration and differentiation. And rather than having to calculate this quite well, in many cases, horrendous limit, what we can do is simply find an antiderivative, evaluate that antiderivative at endpoints, and voila, almost like magic, we get the integral. Now, of course, there are some conditions that we need to check that it can apply, but for a great many interesting cases, those conditions do apply. And it opens up a whole world of integration then for us.
Yes, it's quite a miracle of mathematics that if you think about calculating an integral as taking the limit of the sum of Riemann sums, so of areas. So to do that in practice, you need to do infinitely many computations, which even for the fastest computer would take forever, would never finish. And here we have this theorem which just miraculously reduces this infinite number of computations to something which happens, well, depending on how good you are at spotting an antiderivative,
Yeah.
can take you a few seconds. And even if it takes you an hour, that's still quite an improvement on forever.
Indeed. I mean, it really does make finding an analytic, solid, theoretically good solution very nice and simple. Of course, there are questions for which we can't apply it, and questions for which, well, we can't find an antiderivative. And then you might go back to Riemann sum and say, well, can I make some improved sums? Can I do some things there which at least I can get an approximation, which I know a computer will do in finite time? And those are important things to also bear in mind.
Yeah, I found it as a first year student for some reason, quite intriguing that every elementary function has a derivative, but not every function that is elementary has an antiderivative that's also elementary. So you can't generally integrate an arbitrary elementary function and get as your answer a function that is also elementary, which for me was quite surprising.
Indeed.
Yeah, there's a simpler version of this, which is perhaps not as profound, but I think illustrates the point quite nicely. Is that when you differentiate rational functions, you end up with a rational function always.
Yeah.
But when you integrate rational functions, you can get a lot of different things. You end up getting logarithmic functions. You end up getting inverse trigonometric functions. You end up getting trig functions. All sorts of weird things. And this is so strange.
Yeah.
You start off with this really innocuous little function, rational thing, and then you end up getting this enormous variety of things when you compute the antiderivative.
Indeed, it is quite beautiful. I always enjoy being surprised by mathematics. It's a wonderful thing. So that is the fundamental theorem of calculus part two. But if there's a part two, then surely there must be a part one. What is that?
This is a well, so it's the friend of part two. Part two says if you can find an antiderivative for a continuous function, then you can compute the integral. And part one tells you that there is an antiderivative.
Mhm.
So for every continuous function, there's an antiderivative.
Yes, you can build a function out of that function that you are given that will serve as its antiderivative, that when you differentiate, it has all the properties you want for applying your fundamental theorem of calculus. So it's almost slightly going in the opposite direction.
But the antiderivative need not be an elementary function,
Oh,
of
yeah.
course.
No.
So you can't necessarily write it as a polynomial or an exponential function or using trigonometric functions, etc.
Yeah.
And I believe they will encounter part one in the follow-up course in 124.
Yes, yes. Quite a bit of time is spent on the fundamental theorem of calculus there. It's curious again that these functions whose these elementary functions whose antiderivatives are not elementary functions are not esoteric things that only some weirdo mathematician is going to bump into in a dark alley in the middle of the night. You know, they are actually fundamental things, and the best example is from probability theory, from statistics.
Yeah.
Where an essential, probably the most important function in all of statistics is the antiderivative of e to the minus x squared.
Indeed.
And that antiderivative is not an elementary function.
Yeah.
That's the reason why in the back of your statistics book, there's a table for the normal distribution, because you can't compute it.
Yeah. Okay, fantastic stuff. Then, of course, in our tutorials, where we tackled some of these things, we still battled a little bit with the L'Hopital's rule and doing some pretty crazy limits. I must say, when I was looking at our test for this week, well, for the week just past now that our students just wrote, I was very quickly trying to check it, and I was like, "Oh yes, I'll just apply L'Hopital's rule." And only 5 seconds later, I'm like, "Wait, it's not applicable here." Conditions have not been met. And the point is, this happens to us as well, right?
Yeah.
You have tools that you try and apply them, but you have to build the intuition to see, wait, something's gone wrong,
Mm.
and then be able to say, okay, what has gone wrong?
Yes, if you can, you should have a plan B. Always try and verify your plan A answer using a plan B method.
Indeed, that's one of the things I love about mathematics is so many of the things that we do um, can be quite difficult to build the answer. But once you have the answer, you've got another method to test whether it's the correct answer quite easily. And this is fantastic to have that situation because you can actually quickly test, is that the right answer? But it's sometimes you can't do that, and therefore it's also important to sort of build an intuition about what the answer should be, right? And that's why I always tell students, when you do a limit, the first thing you should do is get a feeling for it. What do you think should be happening as this thing goes there and that thing goes there? And then can we bring the formality to try and prove that that is indeed going to happen?
Yes, I think with these optimization problems, especially before you find the solution, just think about it logically. What kind of answer realistically do you expect?
Yes.
And that'll often help you discard some problematic answers. For example, lengths and dimensions can't be negative in the real
Yeah.
world.
No, I mean, for me, that is often the most dangerous thing that students do, and I understand where they're coming from. It's if you kind of just blindly applying the thing, you get what it spits out, and you give that as your answer without taking a second to actually consider: does this make sense for the question that I've been asked? Does this answer the question I've been asked?
Mm.
Although it can be useful to take the mathematics at face value, I believe that's how Paul Dirac discovered antimatter. In the equations that he was using, they included answers involving complex or imaginary numbers, and he initially ignored those answers because they didn't seem to make sense. But then he began thinking, well, maybe I shouldn't ignore them, and that led to the discovery of antimatter.
Yeah, beautiful stuff. But I mean, that comes again to actually thinking about the things that the mathematics is telling you and trying to relate it. And in that case, there was conflict between the two. And it's from that conflict that beautiful new theory sometimes gets developed.
Yes, I think another example of this is the discovery of black holes. I mean, some particular solutions of Einstein's equations for general relativity predicted the existence of black holes.
Uh-huh.
It's only because of that that people started looking for them.
hmm I mean, another example, which is for me perhaps a little simpler, is the even just the simple idea of complex numbers.
Ah,
Well, it's maybe not so simple. I mean, when people were starting to play around with polynomials, they like square roots of negative numbers. No, this makes no sense. This is nonsense, right? But by investigating that conflict further, we built beautiful, much more powerful mathematics.
yes, and it turns out that the complex numbers are in many cases the right context in which to do things. That the natural thing that should happen happens when you use complex numbers, but it doesn't happen when you use just real numbers.
Indeed.
Even in ancient Greece, initially there was reluctance to accept the existence of irrational numbers.
Yeah.
Oh, yes. Apparently, the Pythagoreans swore that, so they were basically not so much a bunch of mathematicians as mathematicians slash a cult, and they swore the members to secrecy about the irrationality of root 2.
Uh-huh.
And I mean, this was a big shock for them because I mean, you've got it's a right triangle with two sides of length 1, and then its hypotenuse. This is a real object, so if
Yeah.
there are no irrational numbers, then that length should not be irrational. And apparently, the guy who let the secret, the cat out of the bag, so to speak, was sentenced to death by the Pythagorean cult.
Yeah, I know. Mathematics can indeed be quite exciting and interesting at times.
Dangerous, it seems, as well.
Knowledge is dangerous.
Mathematics, of course, is an abstract science. It's not really based on a physical reality. So within mathematics, you should be careful to trust your intuition too much. For example, intuitively, you wouldn't think that parallel lines can intersect, but in some abstract sense, they can. If you take things like projective geometry, they intersect at infinity. And that's, Einstein, when he started working on the theory of special relativity, conventional wisdom was that the speed of light was not constant and that light moved through a medium called the ether.
Yeah.
Although this had never been observed and they'd never successfully detected any variation in the speed of light, but common sense dictated to physicists of the era that the speed of light could not be constant. If it moved with the ether, it would move faster. If it moved against the ether, it would move slower. And Einstein simply said, well, let's assume that the speed of light is actually constant because there's no evidence to the contrary, and he came up with the theory of relativity as a consequence thereof.
Mm-hmm.
Well, so yes, mathematics. Well, it is as it exists now. It is a very abstract science, and with no connection to any specific reality. But it remains remarkably adept at describing reality.
Mm-hmm.
And I think this is not, despite the abstract nature of the subject, but precisely because it is abstract. Because it is abstract, it can describe many things. Whereas if it were concrete, it could only describe a few things.
Yeah. No, and returning to this idea of intuition, I mean, I feel that that is sometimes the places I've learned the most is where you have some intuitive idea, but then when you actually try and rigorously check it mathematically, there's a problem.
Mm.
And that conflict between the two is where I feel I really learn a lot. And of course, then you build your intuition further, and now you've got a better idea of some of the things that can happen and how they happen.
Mm.
Yes, it's a bit like the intermediate value theorem. It seems so intuitively obvious, but try and prove it, and it's another story.
Indeed, and then you have to learn a lot about real numbers.
Yes, I think we can learn as much from our mistakes as we can from our successes.
Indeed,
But then you must not just say, "Oh, I've made a mistake," and then move on. Then you must try and understand why what you've done is wrong.
indeed, and it is very tempting to just. I mean, this has happened to me as well. If somebody marks something that you've got wrong, it's because that guy is just being nasty, or they're being overly strict, or they're just full of nonsense. You can come up with many reasons in your mind as to why you lost that mark, which has nothing to do with you. You actually fine. But that's a dangerous road to go down. Much better is to try and calmly take that and say, well, let's see. They said I got something wrong. Is there maybe something here that I can learn from? And more often than not, there is lots that you can learn from.
Mm.
So, speaking of which, our students got their semester test two back recently. And, well, quite a few of them did really well. But what I found mostly encouraging is it seems that a great many of them managed to really learn, I think, from their previous feedback and to do better this time. And I was very much encouraged that a lot of students managed to improve their mark from the first semester test to the second semester test.
Yes, a few students did quite well. I would say subjectively, I noticed an improvement in the overall quality of answers in the question that I was marking.
Yes.
Yes, I also think that the level of solutions presented were better this time than in the first semester test. And it's important that we're seeing an upward trend.
Yeah.
So students are doing better, and I want to encourage the students. You may not or be exactly where you want to be, but you're moving in the right direction. There's an upward trend. Just keep working, keep trying to improve your understanding of the module and carry this trend through into the exam.
And beyond. I was intrigued in our tutor meeting yesterday. One of the tutors alluded to the fact that WTW 114, he initially found it very tough, quite a shock really, but he said it prepared him very well for his subsequent analysis modules.
Which he then found much easier. I was also extremely encouraged by that comment.
Yeah, students must resist the temptation to partition their studies. You're now doing 114. End of the semester, you write an exam, and you pass the exam, and that's it for 114. 114 is gone. Now you move on to 124. That's not true. The material in 124 is based on what we've done in 114, and just like that, the material you're doing in your second year, you need the solid background from your first year to master it.
Yeah, so I mean, specifically, putting in time now is going to pay huge dividends for your future. If you really start with making your foundation solid, life becomes simpler later because you're then starting from a much better position. All righty, and we are really getting towards the end now. We have really just one more week of lectures to go, and that will be our next week, where we really finish off with the material. So what's left to do is, well, we want to take the integration a little bit further, right? We've set up the basic definition of what is an integral, and we've set up a beautiful tool with the fundamental theorem of calculus for evaluating some integrals. And now we want to, well, take that a little bit further. Can we now go and look at some more complicated functions and find their integrals? And how do we go about that? And then in the last few lectures, we'll also look at some transformations of integrals. And specifically, we'll look at a method of substitution. And this will actually put us in the position to come to prove some of the claims that we made earlier regarding the integrals of odd and even functions. Once we've dealt with those kinds of transformations, we'll be able to prove those properties.
Yes, students should master these basic techniques well, because in their second semester they'll do more integration techniques like integration by parts and trigonometric substitutions and all. And if their foundations aren't solid, then you're going to have a problem in the second semester. So make sure that you get a good grip on these basic integration techniques.
And well, then that will be it for the content we're covering in this course. I almost feel it's a shame we don't get to spend a little bit more time on integration. There are quite a few topics that are right. We're almost touching them. We've got everything built up to do them, like solids of revolution and like the arc length of the curve. These are things I mentioned in the bonus, but I always feel sad that, I just wanted to do a little bit more calculus.
Yeah, the solids of revolution is really pretty application of integration. But luckily, the students will be doing arc length in 124 next semester.
Okay, fantastic.
And in a month's time, many of them will be done with the module.
Indeed, and then we will all rest a little bit easier again.
I think the exam is the 14th of July, is it not?
That's right, I think.
Indeed. At least that is the preliminary date, but we have no reason to believe that will change.
Yeah, but there's so much more to integration that our students still have to discover. I mean, in second year, they'll be looking at integration of functions of several variables. And there are several different kinds of integrals. There are multiple integrals, and then there's surface integrals and line integrals and all sorts of wonderful things.
Yes, so they also then start changing coordinates to see in what coordinate space the integral is the easiest to do. So much beautiful stuff to be done.
And in the third year, if they do complex analysis, they'll do integrals involving complex numbers.
Indeed. I think we'll have to return next week and talk a little bit about, well, what does the future hold beyond 114 mathematically?
Sounds like a good idea. I think it's good for our students to get a kind of a view of things that are coming.
Well, okay. I think that's going to be it for this time. Stay safe out there.
Bye.
Goodbye.
Ciao.